for this. We got it? And this is a good example of having a really cool title across the 2 words. And you guys are gonna, this will be.
Well, thanks for being here, everybody. I am very excited to share the work I've been doing for the past 2 years. So this is the detrital zircon geochronology and history of deformation in the Spokane area's Cambrian to Mesoproterozoic metasedimentary basement.
Down. Sure, it's being weird again.
I don't know, it's not.
Oh, there we go.
There we go. Just had to write sometimes. Okay, so let's start everything off with what am I talking about when I'm saying the Spokane area's metasedimentary basement? Because these are the rocks we're going to be focusing this entire talk on. So at the surface, what we see usually in the Spokane area is the Miocene Columbia River flood basalts, and then our Pleistocene Missoula outburst flood deposits, and that's a lot of alluvium. But what we don't see that often are these minimal outcroppings of Paleozoic and Precambrian metasedimentary units that we're calling our basement rocks. So these are very important. So when we look at these rocks, they are recording about 900 million years of the evolution along the Western Laurentian margin from about 1.45 billion to the Cambrian. So around 500 million is where we kind of cut off this study. But where they are very minimal down in this area, there are abundant outcrops up in the Chewelah area, just about 50 miles north. So if you're looking over at this figure, you can see abundant, all of this metasedimentary basement is outlined in red, but it's much more sparse coming down further. And we have a little graphic here to show why that is. So our Quaternary and Pleistocene deposits on top here, and then our Miocene Columbia River basalts actually cover up what used to be mountain ranges and big valleys, and those flood basalts really filled in those valleys. So all we see is just poking out at the top are what we have colloquially termed the buttes in this area. So more on the geologic setting. Where this study is taking place is the Laurentian or North American Craton. And again, these metasedimentary rocks in Spokane record roughly 900 million years of tectonic evolution. And a lot of this is taking place during what we have coined the boring billion. So if you look over at this figure, these are all of our major provinces that we will be discussing in this study. We won't be going into these provinces in detail, but our source material is going to be originating from these provinces. So they are important to understand where they are spatially and in comparison to where our samples have been found. So starting at the oldest, let's get into what's actually happening on Earth at these time periods when these rocks are being lithified, when all of these sediments are deposited. So from 1.7 to 1.3 billion years ago, we had supercontinent Columbia or Nuna. And this encompassed and consisted of most existing land masses on Earth. So almost all of the land masses were a part of supercontinent Columbia. For this study, we will be focusing on rifting between Mawson and Laurentia when we are talking about supercontinent Columbia. So over here on this figure, you can see this star. And this right here is what we now know as our western margin. Of course, things have moved since then, so they aren't going to be in the exact same orientation. In the Mesoproterozoic to Neoproterozoic, we have supercontinent Rodinia. So this is after supercontinent Columbia. We had rifting from the Mawson continent off the western edge of Laurentia, and Mawson is now what we call Western Australia and Antarctica. So that is rifting off of Columbia. We have an ocean basin, and then at about 1.1 billion years ago, we had a recollision of Mawson with the western margin of Laurentia and possibly Tasmania into there too. So with that recollision, we now have supercontinent Rodinia. And of course, there's also a lot happening at the at our eastern margin as well. But at the end of supercontinent Rodinia, Mawson, and possibly Tasmania once again rifted off of this western margin. And so you can see over here, once again, we have Mawson, there's possibly Tasmania coming right through here. We have a spreading center, and this is the western margin of Laurentia. So after the rifting of supercontinent Rodinia, we are in the late Neoproterozoic to Cambrian. So post-Rodinian rifting, we have a passive margin along our Laurentian, along our western Laurentian margin, or the Cordilleran, after 750 million years. There's continuing to be spreading centers on our Iapetan margin, so the opening of the Iapetus Ocean, and at about 520, we see an emergence of uplift in the middle of the Laurentian craton, and this is known as the transcontinental arch. This ends up being very important further down the road in understanding what our detrital zircon signatures mean for the times they were deposited at. So the uplift of the TCA is concurrent with major rifting along the Iapetan margin. And so that is illustrated well right here. You can see over here in the early Cambrian, we're going to have, this is our Iapetan margin right here. Here's our transcontinental incipient arch. And then here's the transcontinental arch. And you can see a lot of rifting and spreading has happened on that side. So in understanding now a good amount of where the continents were at the time, where we were in the supercontinent cycles, we can start to actually look into what our detrital zircon means. And so a very, very important piece of time is known as the North American Magmatic Gap, or shortened to NAMG. So the North American Magmatic Gap is a time period from about 1.49 to 1.661 billion years ago, where there was quiescence within the Laurentian craton, meaning we were not seeing a lot of material being produced that is native to the Laurentian craton. But what we do see is a lot of material at about 1.58 being produced on the Mawson continent. So it's non-native to Laurentia itself. The presence and magnitude of these North American magmatic gap signatures actually are able to tell us where we are in relation to the Mawson continent and how far away that rifting was when we're looking at supercontinent Columbia and the rifting between supercontinent Columbia. So as Mawson is getting further and further away from the western margin of Laurentia, we see a decrease in North American magmatic gap age populations just due to proximity and the fact that they cannot actually get into these sedimentary basins that we are now analyzing because these sources too far away. So this is a nice little figure. You can see right here, this is around where we are. Here's out Idaho right here. So we're going to be right here. So here's Mawson, and we're looking at rocks that are deposited right in here. And that's the Spokane area. So the geologic units in specific that we are looking at, it's the full stratigraphy, if we look at it with all of these together, goes from the belt supergroup at the base, the Deer Trail group, the Buffalo Hump Formation, and Windermere supergroup. And then unconformably overlying all of this, we have a lot of Cambrian sandstones and quartzites. However, we do not have samples in this area from all of these units. We do have more unconformities down here, or maybe just the outcrops themselves are concealed. So the red stars over here indicate the ones that we have samples from. And so that'll be the Pritchard, Rivali, and Pegan in the belt supergroup, the Togo Formation and the Deer Trail group, and then the early to middle Addy quartzite, which we will get into further. So the belt Purcell supergroup, it is known as the belt supergroup down here south of the border up in Canada. It's the Purcell. Our basal unit is going to be the Pritchard Formation at about 1.45 billion years old. The Rivali Formation overlies that. The Pegan group And then the uppermost unit will be the Missoula group, and that sedimentation ended at about 1.39 billion years ago. And this is recording extensional tectonics within a widened intracontinental sea. So we're not looking at an ocean basin, but we are looking at the Pritchard is going to be it's going to have less extensional tectonics as we get into the Missoula, where we are seeing a lot of widening in our tectonics and more of an ocean basin forming. But we are not quite calling it a sea or an ocean basin yet. So the Western Belt supergroup, detrital zircon populations are primarily falling within the North American magmatic gap. So most of our sedimentation is actually coming from the Mawson continent and is not native to Laurentia. So this clues us in that Mawson itself is very proximal to the western margin of Laurentia and where these basins and where the sediment is being deposited in these basins. The main peak we are seeing throughout the belt supergroup is at about 1.58 billion years, which is consistent with the Roller Craton over on the Mawson continent. And so over here, we can kind of see a Concordia, and that box right there is where the highest density over here. That is the densest point of where all of these ages are falling, and it is in the North American magmatic gap. So, and this one right here is of the Pritchard formation. So this is our basal unit of the belt supergroup. As the belt supergroup is ending, North American magmatic gap populations do kind of fizzle out. They get less and less. There's less magnitude to them as you travel up stratigraphically. And then at about 1.39, there's very minimal North American magmatic gap sediment. So the belt supergroup sedimentation ends at the end of the Missoula group at about 1.39, and this is due to structural uplift and the ending of the Moyer-Purcell large igneous province, and this cross-cuts the belt supergroup. So as we're now into the Deer Trail group, we're over the belt supergroup. So the Deer Trail group sedimentation begins at about 1.37 billion years. So there's about a 20 million year gap of where we call these, whether it's belt or Deer Trail. And this represents a sedimentation source shift from Mawson detritus to mostly native to Laurentia detritus. And at 1.37, Mawson was no longer proximal to the Deer Trail Basin. We have an entire ocean basin between us and the Mawson continent, and there is an overall lack of North American magmatic gap ages in the Deer Trail group as compared to the belt supergroup. So we can see the Mawson continent here. There is an ocean basin coming through here, and here is the Deer Trail Basin. So we are just a tiny bit south of that main outcrop of the basin. So the DZ or detrital zircon populations in the Deer Trail group are primarily around 1.68 to 1.6 to 1.8 billion years. And then other populations that are younger than 1.49. So that's where we really see that North American magmatic gap, where we don't have really much sediment from that age range. So in the Deer Trail group, our basal unit is the Togo Formation. Then we have the Shamokin and the Wabash Detroit, the McHale Slate, and overlying all of that is the Stensgaard Dolomite. In this area, however, we only have samples in the study from the Togo Formation, so that is what we will be focusing on once we get into the data itself. Okay, so our Buffalo Hump Formation and Windermere supergroup is now we're looking at the initial rifting of Rodinia. So we kind of skip over that amalgamation. We don't have much in terms of data from there in our study. So the Buffalo Hump Formation is about 760 million years old. So we see a big jump in time right here, and it unconformably overlies the Deer Trail group. It is very siliciclastic. In a lot of cases, you see it as a big metaconglomerate. And those quartzite clasts are mostly recycled Deer Trail. So there was enough time between the deposition of the Buffalo Hump and after the ending of deer trail sedimentation for enough erosion to take place to see a lot of recycled material in the Buffalo Hump. So the Buffalo Hump itself records the initial rifting of supercontinent Rodinia. So that was when we saw Tasmania and Mawson coming off the western margin of Laurentia after it had reamalgamated on. So the Windermere supergroup were now above the Buffalo Hump Formation younger, consist of the lower Huckleberry conglomerate, the upper Huckleberry lavas, or the Leola volcanics, or all the other names for the Huckleberry. And then on top of that is a very carbonate-rich conglomerate known as the Monk conglomerate. And again, this is recording rifting of Rodinia. And over here, we can also see the detrital zircon populations themselves change to more from a primarily unimodal peak. So there's one main peak in there to a much broader distribution. So this is from one of Dan Brennan's papers. We see grains as young as around a little younger than 780. And then we see lots between here, and it's very spread out. So on top of the Windermere, we have unconformably overlying Cambrian quartzites. So in the late Neoproterozoic to Cambrian, there were a lot of very large sand channels coming all the way from the eastern margin of Laurentia, or the Appleton margin. And this is really where the importance of understanding where we are in relation to the transcontinental arch and where that uplift is taking place and when in time, because we see a lot of shifting of our detrital zircon populations themselves with this emergence of the transcontinental arch. So in our early or late Neoproterozoic and very early Cambrian provinces, we see, again, a much more wider distribution with grains as young as in the Cambrian, really representing that signature. But once we're traveling into the middle Cambrian and we have that transcontinental arch, which cuts off right here, we are cut off from that younger source sedimentation. And we lose really anything before the Paleoproterozoic. So we've had lots of conversations about what to do with these signatures, and we do have some other ways of understanding them, but watching these peaks disappear can really pinpoint where you are exactly in time in relation to the uplift of the transcontinental arch. So let's get into the data from this study. So data from this study, we had 10 of these metasedimentary samples, and we were collecting them from all the isolated outcrops in this region. These were processed for detrital zircon on site at the EWU USGS Cooperative Mineral Separation Lab. All of our uranium lead analyses were conducted at WSU in the radiogenetic isotope and geochronology lab with Jeff Report and Charles Knack. Our age populations and our statistical analyses were done using Garrel's 2008 age pick Excel macros, and then Vermeesh 2018 isoplot R for detritals. So in our methods, we would go out, we'd collect the sample, bring it back into the lab, crush it up into kind of chip-sized material. We would then use a disc mill and pulverize the material down to really as fine as we could get it for these samples. And we would sieve out, and we would then take the less than 425 micron fraction to the next step. So we're already at much less, about less than half of a millimeter in size. So then we would use our water density table, or our zircon table, and that acts kind of like a gold sluice. So we're looking for our densest fraction that will fall in that first group. We then use a Franz magnetic separator to only get the diamagnetic or non-magnetic fraction from that. And from there, we do not have much material in here. You can't even see the grains that are in there. But we would do a methylene iodide float separation. So our zircons would all sink to the bottom of methylene iodide. It is a heavy, dense liquid, and our other minerals that we are not currently looking at would float at the top. So we would take that dense fraction. We then would mount these up on about an inch in diameter epoxy chips and take them to WSU to be imaged and analyzed with the laser ablation. So for this study, we did laser ablation, inductively coupled mass spectroscopy, or LAIC-PMS, or for purposes of me saying that, laser ablation. And so that is what they look like when they're in the mount holder at WSU. And then here's a couple of images of zircons that have been hit by those lasers and the pits that they leave behind. So that material is ablated and travels through the mass spectrometer. And then we get all those ratios, and then we get to deal with all of our data. So after we've done all of this, here is our data for the belt supergroup. So we had 5 samples in the belt that most closely correlated with the belt supergroup, 2 of which correlated with the Pritchard formation. So that's our basal belt supergroup. And you can see those are down here. Here's Bonnie Lake and Flagstone Hill. So here's Bonnie Lake up here, and here's Flagstone. You see a very, very strong peak in the North American magmatic gap, falling almost exactly at 1.58 billion. So beautifully corresponds to the Pritchard formation. Then we go into Rosa Butte, where we have, again, a very strong, but this is Rivali, so it's overlying the Pritchard. Then we have the very lowest bit of the Pegan group is our Fish Lake samples. That is over here. So we're right here. There's Rosa Butte and there's Fish Lake. And then once we get over to Silver Lake, we're in the more upper Pegan group and the Wallace Formation. It's a really, really calcareous, slightly carbonate, gritty rock, and that's over here at Silver Lake. Traveling upward stratigraphically, we're now into our Deer Trail. And so we only had 2 samples from Magnuson Butte that corresponded to the Deer Trail. So we are seeing a very unimodal peak at about 1.68. So before the North American magmatic gap, which very, very nicely corresponds with the Togo Formation. But one of the things that we did have to look into is that we do have a tiny little bit of North American magmatic gap grains in the Togo Formation. So this is different from some previously published papers. So that is at Magnuson Butte, west and east. And then as we're again traveling upward geographically, we have a very large jump in time until we get to our next sample. So right here, we're at about 1.37 billion years. Our next samples that we had were our Cambrian. So we had 3 samples from this study that corresponded to our Cambrian, and that was our Booth Hill up here. And then we have Rosalia and Steptoe Butte down here. So what we're seeing with this data is a very, very strong peak right at about 1.750, so 1750 million. And then other populations in the Archean. So this really clues us in that the uplift with the transcontinental arch had already happened enough to where we were completely cut off from any younger sediment at this point in the Cambrian. So this puts us about at the middle Cambrian. So interpreting this structurally, our Pegan group rocks are being thrust over the Cambrian sandstones right near Medical Lake, and you can see that right about here. And this is due to the Jump-Off Joe Fault. Now, the Jump-Off Joe Fault is a fault between the Belt Supergroup and Deer Trail. However, we are not actually able to see the contact of this fault right here. So we know it is the Jump-Off Joe because it is at the top of the Belt Supergroup. And so our Deer Trail group rocks right here are kind of hidden due to an intrusive material from the Eocene. Compressional environments with isoclinal and stigmatic folding is happening down here with Bonnie Lake and Flagstone. And then north trending normal faults are consistent with our core complex activity. So we have the Priest River core complex over here, and then we have a lot of north trending normal faults that are consistent with that core complex. We were unable to determine exact offset of the Latop fault just due to cover and the restrictions of the data actually collected from this study. So when I was talking about the North American magmatic gap age population in the Togo Formation, it took a little bit of digging for us to actually see this. So initial use of only the Garrel's age pick macros as statistical analysis, we were not able to see these North American magmatic gap grains in the Togo Formation. Age pick uses a 2 sigma error weighted mean. So all of those North American magmatic gap grains were lumped in with the earlier peak, since it was small enough for it to just lump them in with the other ones. But when we're actually interpreting from the raw data itself, such as looking at a density plot in isoplot R, we are able to see that tail of North American magmatic gap grains. So the Togo Formation samples were then compared to raw ages from Box et al. 2020, and you can see that over here. And this is a previously published paper using Garrel's age pick that said there were no North American magmatic gap ages in the Togo Formation, but instead when we were using isoplot R, we were able to actually see those ages even within previously published material. So all three of these do have a very small amount of North American magmatic gap grains. So what does that mean? So this actually has some major implications on our Mesoproterozoic provenance. So before we were saying the Mawson continent was no longer proximal to the western margin of Laurentia, meaning that none of that detritus could actually get over into the Deer Trail Basin. But what we're seeing by seeing a little bit of that is that the Mawson continent was a little bit closer than we thought, and we were actually able to get that sedimentation coming over from the Grawler Craton. This also corroborates the previous model that Mawson itself rifted off the western margin of Laurentia in a counterclockwise rotational way. So if you kind of think about it, if this is Mawson, here's the western margin of Laurentia, it's going to be coming off of it like this. So it's not just pulling away straight like that. And so in other 1.37 to 1.30 billion year old basins, such as the PR1 basin, which is significantly farther north than where we are, we don't see those North American magmatic gap grains, but we do see them down south, meaning that down south at the Mawson continent was more proximal to the western margin of Laurentia for longer than it was in the north. And that's how we can corroborate that rotational rifting motion. So when we're looking at our Cambrian provenance, as I said earlier, a lack of Neoproterozoic and then Stenian age detrital zircon populations, we have changed our previous identification of the Cambrian units in this region from the Addy quartzite, which is an earlier Cambrian, to the Gold Creek quartzite. So the Addy quartzite has a type locality up in Addy, Washington. It's just south of Chewelah, but the Gold Creek has a type locality in Lakeview, Idaho. And so that's just in the panhandle of Idaho. So we're seeing a different unit than we were thinking it was before. And we were able to compare this to other previously published data, such as this is, oops, there we go. So from Lind 2018, here's the Addy quartzite, and this is where we can see that younger population and even another younger population right here. And so those younger populations are showing that that sedimentation has not been cut off from the eastern margin of Laurentia, the eastern side of the Craton yet. But however, when we look into the Gold Creek quartzite, our youngest peak is at about 1.75 billion, even though it is a Cambrian rock. So all of our analyses lined up mostly with the Gold Creek quartzite. We have a little bit more Archean, but that can be variable. So we have identified these as the Middle Cambrian Gold Creek quartzite. So we still have some continuing questions along with this research. As I was talking about before, we had the conversation of how do we actually statistically analyze detrital zircon age populations in order to actually get all of our age peaks and not have any obscured. Because of this study, we have multiple different types of statistical analysis in order to do that, and that's both isoplot R and our age pick program. But there could be another way that could be even better, that we could streamline this a little more. That is something we're still looking into at the moment. And then when we are looking at those Cambrian sandstones, they are slightly, it is difficult to determine the age of them just by looking at the DZ populations. Because we don't have what we call a maximum depositional age, or like one grain in there that is showing at 520 million years old that can really clue us in. We had to do a lot of digging to even figure out if they were Cambrian or Paleoproterozoic, which is quite a large difference. So a question that has been posed is, can the cementing agents in these rocks themselves help us classify samples with difficult to discern detrital zircon signatures? So can the geochemical signatures of the cementing agents, which would have been present at lithification, help us determine what these samples are? Another thing that we will be doing with the Cambrian is going around and collecting all of our late Neoproterozoic to Cambrian samples and then analyzing them to kind of get a good feel of which Cambrian or Neoproterozoic facies were in of those sandstones. So I would like to thank Jeff Revort and Charles Knack at WSU for the help with the analytics. Dan Brennan and Steve Fox for personally helping us with interpretations. Catherine Watts for training and helping us in the lab with the USGS Cooperative Mineral Separation Lab. And then Travis Morton, because he sampled and analyzed the Steptoe and Rosalia samples and really helped to get the EWU USGS lab started. Also, thank you for the funding that was provided through faculty and undergrad research grants through EWU.